Okay, we are now recording, so I think what I'll do is expand the screen to to cover this, and let's see, where did we leave off? I think we were getting ready to start example 2 on page 41. Is that correct?
Yes, sir.
Okay, so for those just joining us or picking up, we're in chapter 2, operations with matrices. Chapter 2 is matrices. Section 2.1 is operation with matrices, and we're on page 41, getting ready to do example 2. Okay, now if my memory's right, didn't Ricky send you a PDF of the book, Jermanuel?
Yes, sir.
Okay, so you have the book, and I think James has the book, right?
Yes, sir.
Okay. We don't know about the new person, if that new person's going to come in or not. They may or may not have a book, so I'll probably do a bit more than normal just because we got a new person coming in. So what I'm going to do, and didn't we do this before, that I did the whiteboard? Did y'all find that better or worse? Hesitating, huh?
About as good as it's gonna get.
Yeah, okay. So we're going to have to live with it. Okay, so here comes the whiteboard. I'm going to do a couple things to the whiteboard first. You can't see this. I have a taskbar at the bottom that gets right in the way. I'm moving that down as far as I can there. And I have a taskbar at the top that sometimes gets in the way. Now, I think this was not one of the classes that I had someone in the class that actually had a tablet PC and could actually write on the board. Y'all don't have one, do you? Neither one of you?
No, sir.
Okay. So I'll be stuck writing on these. Now, do you think my using the draw mechanism where I write the numbers by hand or use the text mechanism by which I type them in? Do you have a preference?
It doesn't matter, whatever suits you.
Okay. Which is easier to read, follow, understand, or less excruciating to watch me work through? Is there a preference? No. Okay.
I don't have one.
Okay. What I think I'll do then is start with the draw, and if it really gets bad, then I'll go back to the other. So here we have two matrices. Example 2, top of page 41. Y'all watching, if you see anyone else trying to get in, let me know. I have so many applications open, sometimes I might not see them as soon as you will. Okay? So, here's the problem. See, it's a lot faster to draw something like that, but the numbers are a bit nasty. So -1, but I'm getting a little better at that. Not great, but a little bit better. 2, 0, 1. There's a matrix. Not good at that either, okay? And we're going to see if we can add it to this matrix. This matrix is 1, 3, -1, 2. Okay. I am getting a little more confident with this. The first question is, can those two matrices be added?
Yes.
Why?
Because they have the same amount of variables.
Okay, they have the same number of entries. That's true. That's not enough. They have to be precisely the same size. This one's a 2 by 2. That one's a 2 by 2. Yes, you can add. This could have been a 2 by 2 and this is a 1 by 4. They have the same number, but no, you can't do that because they're not the same size. Okay, so how do you add 2 in this case is 2 by 2 matrices, how do you do it?
Add each entry, like right here, add A1, 1 to this size, A1, 1.
Okay.
And then this one's A1, 2 to this one's A1, 2.
Okay, so what do we get for the first one?
Negative 1 and 1 will be 0.
All right. We get nothing. Okay. We get a 0. Next.
5. 2 and 3 will be 5.
All right. We get a 5. This is not going too badly. Then we get a
0 and negative 1 give you
negative 1. And then we get a
1, 2 give you
3. Okay. High level math today, huh? All right. Perfect. They took a lot more steps to get there, but if I'm writing on a screen, I'm going to take as few steps as possible. So yeah, we got 0, 5, negative 1, 3. Any questions on that? Yay or nay? Okay, I'll take silence to be consent. Okay, so let's do the next one. The next one is a matrix 0, 1, negative 2. Second row, 1, 2, 3. Very creative there. Okay. And we're going to try to add to that another matrix, which would be 0, 0, 0. A very creative matrix there. Notice I'm not slashing my zeros anymore. It's hard enough to write a 0 with this thing. To slash them, it's even worse. These are ugly zeros. Of course, anytime you make a 0, it's ugly, isn't it? Okay, never mind. Okay, the question is, can you add those two matrices together? Can you?
Yes.
Absolutely. Why? They're
same size.
Exactly the same size. They're both, what size are they?
3 by 3. 3 by 2.
Say that again.
2 by 3.
2 by 3. They're 2 by 3 matrices. 2 rows, 3 columns. Both of them exactly the same size. You can do it. Now here's a tough one. Can you add those?
Yes.
What would it be?
0.
0.
1.
1.
Negative 2.
Negative 2.
1.
1.
2.
2.
3.
3. That was hard, wasn't it? Adding by 0 is always tough, okay? Now, just like 0 in real numbers is called the additive identity element. When you have a matrix that's all zeros and is of the right size, that's called a 0 matrix. Well, it's always called a 0 matrix, no matter what size it is. But if it's the same size as the thing you're adding to, then when you add a matrix to the 0 matrix of the same size, you get the same matrix you had to begin with. So therefore, the 0 matrix is also called the additive identity element in matrices. Okay? Just like 0, the number, is the additive identity element in real number addition, and any kind of addition, the 0 matrix of the right size is the additive identity element in matrix addition. All right, here's C part. Here's a matrix, and it's 1, negative 3, negative 2. Okay. Is that really a matrix?
Yes.
Yes, it is. What's another name for it?
Column matrix.
Column matrix. How about another name for It could be called a column vector as well.
Yeah.
Okay, a column vector. So I'm adding it to another column matrix. Can you add those two together?
Yes.
Okay, and what do you get then?
0, 0, 0.
All right. That wasn't too hard either, was it? Now, just like in real numbers, when you add, let's just take it, a 1 to a negative 1, you get 0. Why? Because negative 1 is the additive inverse of positive 1. Positive 3 is the additive inverse of negative 3, and so on. Those are called additive inverses. Well, if you have a matrix, whatever size matrix, and you have the same size matrix, and every element in that matrix is precisely the additive inverse of the corresponding element in the first matrix, then when you add those two matrices together, you get the 0 matrix of that same size, and that makes this matrix, that second one, the additive inverse of the first one, or the first one the additive inverse of the second one. So those properties that we had for adding real numbers also, so far, work for adding matrices. They just have to be the same size. Okay? And here's the D part. Okay? Here's a matrix. And that's a 2, 1, 0. Add to, and 4, 0, negative 1. Now when I write them close like that, don't think that that's 210. These are matrices, those are individual elements. If I had a double or triple digit element, I would have spread them out more. Okay? We're going to try to add to that this matrix, which is a matrix, 0, 1, negative 1, 3. What's the sum of those two matrices? Ooh, even though it has a ugly black bracket on it. What's the sum? Trick question.
It's not the same size. So
not the same size. You cannot possibly add those two matrices together. This matrix addition is completely undefined. You can't do it because they're not the same size. You're absolutely right. That is an undefined problem, an ill-posed problem. You can't do it. Perfect. Now, that's matrix addition, a very important, useful. You're going to run into this a lot in the later in this course, over and over and over again, when you're adding two entities, whether it's matrix addition or any kind of addition. Okay? And here's the other one that goes with it. The definition of scalar multiplication. Now, I can't write subscripts, type subscripts, so I think it might be better for, oh, both of you have books, don't you? Is it okay for me to just read this to you and not type it out? I know Ricky has a book, and I don't know about the new person coming in, if that person has a book yet. I keep thinking in the back of my head it's a female, so I'm going to say she, but if it turns out being a guy, sorry about that, whoever that's coming in. If you don't have a book yet, see if you can lay your grubbies on one, okay? Here's the definition of scalar multiplication. Let's say we have a vector A. Remember, we name our vectors, matrix. We name our matrix usually by capital letters. So matrix A, capital letter A, we can also name that to be open bracket A sub ij, okay? And since, Emmanuel, you are fairly new at that, let me go on and do this. You can name a matrix by a capital letter name. That's perfectly fine. Or you can name it this way. Just a single bracket and with a single entity in it, that's what I meant to say, but then with a dual subscript, I, J. Now, I and J, by the way, are always integers, not just integers, positive integers, okay? We call them natural numbers or counting numbers. They're just more specific than an integer, okay? And this is both naming a matrix. What this says, every element in this matrix A, however many it has, if it has m rows and n columns, that means this I could be anywhere from 1 to m, because that number gives you the identity of the row, and the j can be any integer, any natural number, any counting number between 1 and n, the number of columns. So this is another way to say that matrix. So here you have a matrix. You can either call it capital A or little a ij. And this is an m by n matrix that gives the size, m rows, n columns. Okay? C is a scalar. What do we mean by scalar? Any real number in the world. Any real number. Positive, negative, fraction, decimal, zero, rational, irrational, it doesn't matter. So far, we're not using complex numbers. And we probably won't use complex numbers. One major reason we won't is I in the complex number system means the imaginary element, which is square root of -1. We're using I for a completely different reason, so we're not going to throw any I's in here. That would really mess up the system, okay? We're going to stay in real numbers. So C is any scalar. By the way, these little a's, they can be any real number in the world too. Positive, negative, fraction, decimal, zero. As we saw here, zeros can easily be in that. We had all integers here. You could have fractions, decimal, irrational numbers. It doesn't matter. Again, we're not going to put any complex numbers in there. Not yet, not in this course. Okay? So C is a scalar. Then we say the scalar multiple of A by C is the m by n matrix, same size as what we started with, and that matrix will be C times A. Okay? It's that simple. The scalar multiple of the number C to the matrix A, CA. Now, here's what that means. That means not just one row or one column, every element, every entity in that matrix is multiplied by the number C. So that's C times Aij. This is getting worse and worse, isn't it? Okay. In other words, that constant C is multiplied by every integer. For instance, give me a C, any C. Make up a number C. Anybody? Anybody?
3.
3. Okay, what if you had 3 times this matrix right here? That would be 0, 3, -6, 3, 6, 9. Multiply every stinking element in, well, they don't have to stink, every element in that matrix by that number C. Okay? It could have been 4/3 pi. It could have been negative square root of 2. It could be anything. Multiply every element by that number. Those are stinking numbers, by the way. Anyway, okay. So that's scalar multiplication. Now, another ramification of that, what if your C was the number -1? So then this scalar multiplication would be negative A. Goodness, they're coming out bad, aren't they? Would equal, multiply every element, Aij, every element by -1. Okay? Well, guess what? That would have given you this. If you multiply this happened to be a column matrix or a column vector by -1, you'd have gotten this one. Okay? That is the opposite or also the additive inverse of matrix A. Okay. Now, here's something else. What if we then have two matrices, A, that came out a little better, and B. Now here's the only requirement for A and B. A and B must be of precisely exactly the same size. So if they're the same size, we already know from up here you can add A and B. The question now, can you subtract? Can you define A minus B? Now there's a bunch of new rules that you have to do subtraction. No, here's the only new rule you have to do. That's the same as adding matrix A, just like it is, to the opposite or the additive inverse of B. And guess what? That's exactly how we added signed numbers. Remember? If you're adding -3 plus 7, no, I said it backwards. Let's do 7 plus a -3. That's the same as 7 minus 3. That would be the same as 7 plus a -3. Same thing with matrices. To subtract two matrices, keep the first exactly like it is, add to it the opposite of the other one, the additive inverse of the other one. Just negate every element in the second one, and you've got it. So that then leads us to be able to do matrix subtraction. It's just the same as matrix addition. You're just adding the additive inverse or the negative of that second matrix to the first. So, any questions before I clear the slide? Everybody got it? Okay, I'm going to clear all my drawings, if you can call those drawings. Well, I'm going to try to clear all the drawings. Well, if I hit the right key, it probably would have worked. Okay, it did finally. Okay, so here's a matrix A. This matrix A is going to be ugly, but okay. 1, 2, 4. That's a 4 there. It doesn't look like it, but it is. A -3, 0, -1. And 2, 1, 2. Either of you used to play basketball? That was one. That was one of my one of our zone defenses. Okay, 2, 1, 2. Two people up front, one in the middle, and two in the back. That was a zone defense that we used to do. B. I wasn't any good at it, by the way. I was okay on defense, but I couldn't shoot, and guess what? I couldn't jump. Okay, never mind. We won't go there. Okay, now here is matrix B. Two, 0, 0. One, -4, 3. This is about as much fun as watching paint dry, isn't it? If I could write. Okay, I should stop saying stupid things and just focus on what I'm doing. Give it up, that'll never happen. Okay. 1, -4, 3. I almost had it right. -4, 3. And -1, 3, 2. Okay, I hope I wrote it right. I know it's ugly, but I hope I wrote it right. Now they want us to do two things or three things with this. First thing they want us to do is find 3a. That's the scalar multiplication of the scalar 3 times the matrix A. Can anyone just tell me what to write down as that answer? Please say yes.
Yes.
Okay, thank you. Now tell me what it is.
You multiply 3 times each.
Absolutely. And what do you get?
3.
3.
6.
6.
12.
12.
-9.
-9.
0.
0. Oh, I could have done that one. Okay.
And 3.
-3. Okay. And
6.
6.
3.
3.
6.
6. That's an illegal defense in basketball. Okay, never mind. All right, that's the first one they asked for. What is 3 times A? Next thing they asked for is what in the world is -b? Can you do that?
Yes.
Okay, so -b would be what?
-2.
-2.
0. 0.
Got it. First row. Second.
-1.
-1.
+4.
4.
-3.
-3.
1.
1.
-3.
-3.
-2.
-2. Perfect. The third thing they asked for is what is 3a. That's pretty ugly. Minus b. What would that be?
Would start off being 1.
It'd start off being a 1. Perfect.
6.
6.
12.
12.
Then we have -8.
Wait. Okay. My pen quit doing right. Okay, there we go. Okay, say that again.
Would it be -8?
Don't think so. Now, B was 1.
Oh, it'd be negative.
Yeah, it's negative what?
10.
-10. You see, they've sort of almost muddied the waters for you. They already did the minus B, so all you have to do is add the 3a to a minus B, and you got it. Okay, next.
Oh, look. Yeah, you're right. We have. What I'm looking at now. Oh, there we go. Would it be 4?
4, perfect.
0.
Huh?
No, -6.
-6, right?
I'm looking
Next.
at the other one. Alright. Well,
Third row.
it'd be 7.
Got it.
0.
Got it.
And 4.
Okay. Yeah, you write better than I do. Okay, I thought that was a 0. It is a 4. I'm going to try to cover my error here. Aha, look at that. I almost did. Okay, that's a 6 and a -2 is a 4. Okay, perfect. Way to go. Now, I sort of wish they hadn't have done something that was so obvious here. If they hadn't have done that middle 2 steps there, what you could have done was taken every entry here, multiply it by 3. 3 times 1 minus 2. That would be 3 minus 2 is 1. 6 minus 0 is 6. 3 times 4 is 12. Minus 0 is 12. And you could have done it point by point. 3 times minus 3 is minus 9. Minus 1 minus 10. You could have done it entry by entry by entry. But they had us do They did the first part for us, did the second part for us. All you had to do was add those two together, which is correct. They took a lot more room. I'm not about to take that much room, but that's what they got. 1, 6, 12, negative 10, 4, and negative 6, 7, 0, 4. Any questions on that? All right. We're ready now to move. Oh, goodness gracious. Matrix multiplication. That's got to be just as easy as matrix addition, subtraction, right? No. Okay. Here's what you can't do. If you're trying to multiply A times B, number one, we haven't gotten there yet, but that would be a legal move. But guess what it's not? It's not 1 times 2, 2 times 0. No, it's not that. Nowhere close to that. Now, I don't know if this is helpful or not, but it helps me remember why. Okay? When you're adding, you truly do add digit to digit, digit to digit, digit to digit, right? But let's say we're multiplying. Now, I'm going to not really make up a number. I am kind of, but I'm going to multiply 124 by 200. I'm going to make it 211. Okay. Now, if I'm multiplying those two numbers, and I know y'all have calculators and you've never operated without a calculator, and you don't know how to operate. No, I'm just kidding. Back in the old days, how did you multiply those two big old numbers together?
4 times 1, 2 times 1, 1 times 1, 4 times 1.
Yes, you're exactly right. 1 times 4 is 4. 1 times 2 is 2. I'm not going to do it all, but I'll get started. 1 times 1 is 1. Then you did the next one. 1 times 4 is 4. 1 times 2 is 2. And 1 times 1 is 1. But you went over 1. And then you did the next one. 2 times 4 is 8. 2 times 2 is 4. And 2 times 1 is 2. And then you proceed to add the numbers together that are on top of each other, and that would be a 4. Okay, I'm not going to do all of it, okay? Now, you did a different process of adding those two numbers together. Adding them, you just add 4 and 1, add 2 and 3. You didn't just multiply somehow and get it. You had a whole different process. Well, matrix multiplication is the same way. You don't just multiply the corresponding entries. You have a whole nother bag of worms to do. Now here, supposedly, is going to be it's kind of an example to give you a clue of how to do this. Let's say you're at a football stadium. Not going to happen anytime too soon, but let's say back in the old days when you could, and this was not Bryant-Denny Stadium. This was a little old school, maybe like a high school field. I don't know where you went to high school. We basically had stands on one side and stands on the other side, and that was it. This was a little upgraded to high school. They have stands on one side, stands on the other side, and on one end, they have another set of stands, okay? They don't have it all the way around, okay? So here's what we've got. And I'm going to abbreviate where possible. This is the south stands. This is the north stands. And this is the west stands. They don't have an east stands. I'm kind of grateful for that. Okay? Now, what our matrix is going to represent is number of peanuts sold, or bags of peanuts, I guess it is, not individual peanuts, sold at each stand, the number of hot dogs sold at each stand, and the number of sodas. This obviously was not from the South. In the South, we'd have said Coke. No, we don't need that. The sodas, we would have said soft drinks, or we would have said something. But sodas is what they say somewhere else in the country. Okay? That's going to be what our columns represent. Okay? Now, since you're selling them, you had to have a selling price. So the column here is going to be the selling price. And that's going to be in dollars. Okay? And here, the rows represent the price for each bag of peanuts. If I could get my pen to write. Each hot dog you sell. You don't sell those by the bags. And each soda that you sell. Okay? Now, the South Stands had sold 120 bags of peanuts. These are for the healthy eaters. Okay? They sold 250 hot dogs. They had a bunch of people who were not quite so healthy eaters. Okay? That would be me. Okay? And sodas, they sold 305 sodas. Thirsty people over there, they're yelling a lot. Okay? This is agonizing, isn't it? In the North Stands, a little healthier group there, it seems like. They bought 207 bags of peanuts. They bought 140 hot dogs. And they bought 419 sodas. Well, think about that. I mean, this isn't a realistic problem, but it could be. The North Stands are facing south, right? So they're getting that hot summer sun. The South Stands are facing north. They may be in the shade some, so maybe that's why they... Oh, that was... There, you let me do it. See, I was doing something stupid talking about the stands, and I wrote down the wrong number, and you let me get away with it. Shame on you. That was 419, not 413. I don't know where the 3 came from. Maybe I took the square root of 9. I don't know. Okay, in the West Stands, they're smaller stands. They only sold 29 bags of peanuts, 120 hot dogs. Boy, this must be the cheaper seats. Okay, 120 bags of hot dogs, 120 hot dogs, and 190 sodas. And of course, this was probably in the afternoon, so they were in the shade. Okay, I'm just making that part up. Okay, what was the selling price? Selling price for peanuts was $2 a bag. Okay, selling price for hot dogs was $3 a hot dog. And the selling price for sodas, which are such a ripoff, are $2.75. Which, in most fields these days, are probably a cheap price, but still a ripoff. Okay. Now, how do you figure how much money you made? By each stand. Okay? Well, South Stand sold. I wish I had 2 markers here. I don't. So you have to do 120 bags of peanuts for $2 each. That would be $240. 250 hot dogs for $3 each. That would be $750 worth of hot dogs. And 305 sodas for $2.75 each. I don't know. That's something close to $900 for sodas. Okay? North Stands, you do the same thing. You multiply this one by that one, this one by that one, and this one by that one, because this is number of sodas times the price per soda. The West Stand, you do this times that, this times that, and this times that. Okay? So, what would your answer be then? Your answer would be, and you add those up too, because you're trying to find out how much revenue you got, so this is how many dollars revenue, that's a pretty ugly dollar sign, you got from the south stand, from the north stands, and from the west stands. Okay? And whatever you added these up, 240 plus 750 plus whatever that was, that's the number that goes here. Okay? That makes sense monetarily, right? Okay. Now notice what's happening here. You multiply every row here by every column here. Every row here by every element in this column here. Every row here by the elements in this column. So what's required, and by the way, look at these two matrices. They aren't the same size at all, are they? This one's a 3 by 3, right? That's not a plus sign, that's a time sign. This is a 3 by 1. And your answer over here is also a 3 by 1. Now, here's what's required. Notice when you're multiplying this, you're multiplying by that, right? So guess what? The number of columns of this one has to equal the number of rows of this one. So in other words, the last number here has to be the same as the first number there for you to do matrix multiplication. And what's your answer? Your answer is going to be what's left. A 3 here by 1 there. And sure enough, that's what you got. So this is how the sizes of matrices multiply. They don't have to be the same size to multiply them, but what you have to have for the first matrix, you have to have the same number of rows in the first matrix as you do columns. I'm sorry, I said it backwards. Same number of columns in the first matrix as you do rows in the second matrix. So those two numbers cancel out. And that leaves you a product that's made up of the number of rows of the first one by the number of columns of the second one. And that's exactly what you get here. Now, they actually did the math. If you would find it instructive, we can do that. But I'd just as soon not write it down. Okay? Are y'all okay with that? And by the way, it's not hard to do mathematically because you're just entering numbers. All right. I just read something about Drew Brees. He finally came to his senses a little bit anyway, or maybe was forced to. I don't know. Okay. So what do we do? Let's do what I said we were going to do. That's 120 bags of peanuts times $2 each plus 250 hot dogs times $3 each plus 305 sodas times $2.75 each equal, and the first number they put there, $18.25.75, exactly like they had in the book. And you put that right here. I said I wasn't going to write it, but I guess I will at least write that first one. Okay? It's really painful, but I'll do it. 18.28. The reason is it's got a lot of digits and a lot of decimal numbers. 0.75.
Okay, now I see how we did it.
What's that?
I'm catching on how we did it.
Okay, good deal. Then you do the next. I'm not going to write the next one, but what you do, 207 times 2 plus, is that a 140 or 190? 140 times 3 plus 419 times 275. equal 1986.25. Yes, they got it right. And then you do the same for the north. So this represents, okay, so notice what you got. You got stands here, product here, multiplied by dollar amount, sale price, product on the rows. The product times sale price gives you money. Well, what you had here was dollars, and what you had here was stands. And sure enough, that's what you get here. So you write those down. That's how you do your matrix multiplication. Now, you weren't asking for total revenue. All you're asking for was how much revenue did each stand produce from those three objects they were selling. Okay? And we've answered the question. Okay. Now, sorry, I may have to drink some water. Yeah. For some reason. Okay. So, definition of matrix multiplication. Now, nobody else has tried to come in yet, have you? Y'all haven't been keeping them out, have you? No, we still got the two. Okay. All right. Definition of matrix multiplication. If A, matrix A, represented by little a ij, that means I rows, j columns. That's an M by N matrix. Matrix B is represented by Bij. Now, even though we use the same subscripts there, that doesn't mean they have the same values for these two. Because B is not an M by N matrix, it's an N by P matrix. Okay? I think I better write this down. Okay? It's painful, but I'll do so. So here we have A. I may just erase what I've got so far just because I don't want to crowd up the slides too much or the page too much. So here's what I've got. Here's matrix A. Capital letter A stands for a matrix, and that can be represented this way. A representative element, little a, with subscripts I, J. Okay? Now this matrix here is an M by N matrix. M by N. What does that mean? M rows by N columns. Okay, that's always what we mean when we say M by N. First number listed is the number of rows. The second number is the number of columns. Then we have matrix B. Capital letter represents a matrix. And written as another way, you can express that as Bij. Okay, little b, that stands for each individual element there, and we're I and J. Now, just because these are the same letters, they won't necessarily have the same value. They just mean those are your counters. I counts the number of rows, J counts the number of columns. Okay? But this size for B is, if it was M by N, and M by N are different numbers, M and N are different numbers, you can't multiply. But if B is an N by P matrix, what's required is the number of columns from A must equal the number of rows of B. Okay? If that's the case, you can multiply. If it's not the case, you can't. Even though M by N is the same as M by N, no, you can't multiply them. You could add them, you could subtract them, but you can't multiply them. To multiply, the number of columns of the first must equal the number of rows of the second. Okay? So that's a N by P matrix. Then the product matrix, which we'll call AB, meaning you've multiplied A by B. Okay? Now what size will that be? Well, like we said, the number of columns here must equal the number of rows here. So this product matrix is going to be an M by P. So it could be a completely different size of either one of the other two. That would be the result. Now that's the sizes of the result. And that matrix, they're going, basically, it's like they're calling it matrix C, but they're not giving it that capital letter name. They're just saying its entry is Cij. Okay. And in this case, now this is the really hairy way to write it. Okay. Now, if you lose the brackets there, which I'm going to pretend that we've lost them because that represents the entire matrix. But if you're just talking about the element Cij, that's the summation of this. Now, this is a hairy way to write this. Summation from K, a completely new counter. It's going to start with the number I and go to the number n. Well, n was that number of columns here, number of rows there, the thing that we threw out. So this is what k is counting from. And what are you multiplying? Or what are you summing? You're summing a, and it's going to stay I, but its second counter is now going to be k. It's going to start at 1 and go up to n. Well, that's how far j went, from 1 to n. And multiply that by the element from the B matrix, B, and it's going to be from k, starting at 1 and going up to n again. So this is going to be the k element, the row number, but this will remain the j. Okay? Now, on the line below this, they write out what some of these are. A I1 times B1J plus AI2 times B2J plus AI3 times B3J plus, and you keep on going until you finish all of the numbers from 1 to n, and then, so you have BIN times BNJ. And you do that for every IJ pair that you have, and that's what you get. So there's a lot more involved with multiplication than there is addition. But it's just like multiplication of numbers. You multiply every digit by every other digit in every way that possible. You're almost doing the same thing here. So let's do an example. Okay? So much for the blah, blah, blah. Let's do an example. Okay. Here's a matrix A. I should have brought up some soda because I am so hungry. I've been teaching since 8:30 this morning, and it's way past, or it's right at what time I usually try to eat. That may not be big enough. Let me see. A is negative 1, 3. Four, negative 2. And 5, 0. It's an ugly 5. And that's a 0. There's matrix A. Here's matrix B. It's a negative 3, 2. And a negative 4, 1. That's a 4. It's a pretty ugly 4. Now here's the question. Can you multiply these two matrices? A times B. Okay, that's the question. Here's how I go about answering the question. I write down the size of the matrix. What is the size of A?
Is it 3 by 2?
3 by 2. You're absolutely right. Write it down. I do anyway. You don't have to. You can do it in your head. What's the size of B?
2 by 2.
It's a 2 by 2. Now, what's required for us to be able to multiply those two matrices together? The inner digits have to be the same, and they are. So the answer to the first question, yes, you can multiply these two. Now, here's the second question. What will be the size of the product matrix? It's what's left over. 3 by 2. Okay? So it's going to be a 3 by 2. I don't see the book doing this, but I like to cross these two out. They have to be the same number. If they're not the same number, hang it up. You can't multiply them. But if those are the inner two are the same numbers, then cross them out, and the size of the product is going to be the first here by the last here, 3 by 2. Now, here's what I do next. I represent me a 3 by 2 matrix. Okay? Now, what is a 3 by 2? It's going to have 3 rows and 2 columns. So that's going to represent a 3 by 2 matrix. Now, if I were writing these, this works okay. Now that I'm using my finger on the pad, I may quit doing the lines here because they may get in the way and get really ugly. Okay? But that's how I like to do it. Okay? Now, here is my next step. You could go back and do those I, J, K things if you wanted to. Here, to me, is a simple way to do it. I want you to tell me what the name of this entry is going to be. They've been calling that the letter name C. What are the subscripts for this entry right here? Where is this located? First row, first column, right? This one right here is first row, first column, right? Okay. That means I'm going to take the first row of A and multiply it by the first column of B, adding them up as I go. Remember, that's how we did it when we multiplied numbers. You multiply first, and then you wind up adding them, right? Going to do the same thing here. So it's going to be a minus 1 times a minus 3. That gives me 3 plus 3 times a negative 4. What's 3 times negative 4? Say again?
Negative 12.
Negative 12. So positive 9, wait a minute. I got lost. 3, positive 3 minus 12 gives me negative 9. There's your first entry. The 1, 1 entry here is the product of the first row here by the first column there. Now, what's the address of this one? This entry right here. What's its address? First row, second column, right? This entry.
I was trying to see what you was pointing at.
Say again? Oh, okay.
I was trying to see what you was pointing at.
Can you see my little pencil?
Right.
Okay, yeah. That entry there is first row, second column. So that's exactly what I do. First row of A by the second column of B. So the first row is a minus 1 times 2 is negative 2 plus a 3 times 1, 3. Negative 2 plus 3 is 1. Perfect. What's the address of this one right here? Where are we, Waldo? Second row, first column, right? So second row of A, 4, -2, we're going to multiply by the first column of B. So that would be 4 times a -3 is?
-12.
-12. And then a -2 times a -4 is?
-8. No,
positive 8. So -12 plus 8 would be?
-4.
-4. Perfect. Okay. Now, if you haven't noticed yet, matrices, what we did in the last chapter, what we're doing now, they're usually pretty simple mathematical operations, adding and multiplying, okay? However, you got a whole lot of them, and you got a lot of opportunities to make little silly mistakes. Don't do it, okay? This entry here, this is second row, second column. So we take the second row of A and multiply it by the second column of B. So 4 times 2 is?
8.
8. And -2 times 1 is?
-2.
-2. 8 minus 2 is? 6. Perfect. Okay, this address down here, third row, first column, you do the third row of A times the first column of B. 5 times -3?
-15.
Plus 0 times -4?
-4.
0 times -4?
Oh, 0 times.
Yes, yes. 0.
0.
So that would be a -15, right? Like I said,
Lots
lots of simple operations, but lots of places to make a silly mistake. Okay? It wasn't that silly. Okay. What's this entry here? Third row, first column. So take the third row of A, 5, 0, multiply it by the second column of B, 2, 1. So 5 times 2 is? 10. And 0 times 1 is?
0.
0. So that comes up a 10. All right, we just multiplied our first two matrices together. Let's see what we got. The book took a whole page to do that, and they got -9, 1, -4, 6, -15, 10. Yes, yes, yes. Okay? Now, by the way, before we turn the page here, here's a guy named Arthur Cayley. Okay? Now, why did they bring him in? Well, he was a British mathematician credited with giving abstract definition of a matrix. Cambridge University graduate, a lawyer by profession, but he did his groundbreaking work on matrices as he studied the theory of transformations. Also instrumental in the development of determinants. We'll talk about those in the next chapter. And he and two American mathematicians, Benjamin Peirce and Charles Peirce, their father-son, credited with developing matrix algebra. So if you want to curse somebody, don't curse me, curse them. No, I'm sorry, I didn't say that, did I? Okay. Now, guess what? You may choose to write on either Arthur Cayley, matrix multiplication, theory of transformations, Benjamin Peirce, his son Charles Peirce. Lots of different paper topics just in one little blurb. So, hint, hint, be thinking about, start working on your papers. By the way, in 2 classes, 1 person each has already turned in a paper, got it in the month of May, so they get 2 bonus points, those 2 people. You get it in the month of June, you get 1 bonus point. You turn it in the month of July, you get your score. Okay? No bonus points added. Okay. So please do it. Now, what they say at the bottom of the page is what I've already been saying. I'm going to show it to you here if I can find it. Can you see that at the bottom of the page? Nope. Wrong place. Am I on the right page? I think so. Okay. Yes. If you're multiplying 2 matrices together, one's an M by N, the others are N by P. Throw away the middle terms, the two that have to be the same, the N's, and then your product matrix is going to be an M by P. Why they waited till now to tell you that, I told you already. Okay? And then once you determine the size, draw it out there. Now, if you don't like putting the lines under it, you don't have to, but just somehow note you've got to have M rows by P columns. So do your little thing. I like doing the lines there. They kind of get messy here when my writing is so ugly. But James can tell you it's always been ugly. Oh, Manuel, you can tell him it's always been ugly too, okay? Yeah, I heard you agree to that. Okay, yeah, I'll remember that. Okay. So, anyway, that's how you do matrix multiplication. Now, I'm really eager to write down on this screen, this one. Aren't you looking forward to me write that equation down? Please say no, okay? You don't want the misery of seeing that, okay? That would take me the rest of the period to write that down. What are they showing here? They're showing for the ijth entry in the product matrix, C, you do the ith row of A times the jth column of B, and that gives you the ijth entry in C. Now you multiply the numbers, adding the products as you go. Remembering not to add the things and then multiply. No, don't get them all crossed up. Take your time, do it right. Okay. Now, there's a little discovery thing here. Sometimes these are really fun and interesting and instructive. Other times they're a real pain in the neck. These look small enough that they should be easy to do. Okay? So let's do it. Here's two matrices. Matrix A, it's not easy to write, is a very creative matrix. It seems like maybe James came up with this one. 1, 2, 3, 4. Yeah, you did it, didn't you? 1, 2, 3, and 4. Okay, really creative matrix there. All right, here's matrix B. Okay, 0, 1, 1, 2. A little more interest maybe, but pretty simple numbers. 0, 1, 1, 2. Now they're going to ask us to do a couple of things here. First, do A plus B. That's not going to be too bad to do, I hope, is it? A plus B. Can you do that? That's the question. To add two matrices, what's required?
Same size.
Same size. And what will your sum be? The same size. Okay? So let's add them. What do you get?
1,
1,
3,
3,
4,
4,
6.
6. Perfect. Okay? Now we're going to do something else. We're going to do B plus A. Can you do that?
Okay.
Of course you can. If they're the same size one way, they're the same size the other way. And your result is going to be the same size, isn't it? As both of them. Okay? And can we do that math? B plus A. What would you get? Say again?
1,
1,
3,
3,
4,
4,
6.
6. If you got the same thing, why'd you have me write it twice, huh? You're just cruel to me, aren't you? Okay? They are exactly the same. Now, this is just a real simple example, but what this suggests to you is that addition of two matrices, if you can add them, if they're the same sizes, you can add them. It doesn't matter which order you add them. We call that the commutative property of addition. It was true with numbers. It's true with matrices. Okay. Now, let's now see if we can do A times B. Okay, the first thing we ask ourselves, can we even do it? And how we answer that is by writing the sizes down. What size is A? 2 by 2, right? Okay, what size is B? 2 by 2. Okay, what's required for us to be able to multiply them is that the two inner numbers have to be the same. Yes, that's a 2, and that's a 2. So throw those out. What size is your product going to be? 2 by 2. Well, that worked out okay. Now, do you want me to draw the lines in there or not? Is it helpful to you? It was, okay. So let's write them in there. It's a 2 by 2, so that means you have 2 rows and 2 columns. Okay. Now, what's the address of this one? That's the first row, first column. So you take the first row of A and multiply it by the first column of B, adding up the products as you go. 1 times 0 is 0 plus 2 times 1, 2. 0 plus 2 is 2. Okay, this is the first row, second column. So you take the first row of A again, but this time by the second column of B. 1 times 1 plus 2 times 2.
4.
That adds to 5. Perfect. Okay. Now this entry down here is second row, first column. So we take second row of A times the first column of B. 3 times 0 is 0. Plus 4 times 1 is 4. Okay, 0 plus 4 is indeed 4. Okay, this entry here is the second row, second column. So we take second row of A, 3, 4 times the second column of B, 1, 2, and do them as you go. 3 times 1 is 3 plus 4 times 2 is 8, and 3 plus 8 is 11. Okay, hold on just a minute. I need to turn on my ceiling fan. This morning it was just a little cool for the fan, but now it's beginning to warm up a little bit. Okay, now the next question is, next thing they ask us to do is do B times A. Now the first question for me is, can you do it?
Yes.
Yes, you can. Now here's what I'm going to do. Okay? You don't always have to do this, but I found it easy because I tend to make mistakes. Okay? I'm going to write these in the same order we're trying to multiply. So I'm going to repeat my A over here. Okay? Just write it down on this side so it'll be easier for me to follow. Now, you are probably a lot smarter than I am, so you don't have to do this. But I tend to make mistakes, as you have seen, and so I'm going to write it down here. Okay, there's A on this side. So this time we're doing B times A, and sure enough, A is a 2 by 2, just like we had before. And I do this every time just to keep from making mistakes. The inner numbers are the same, so your result is going to be a 2 by 2, just like it was before, because they're the same sizes, and they're square. That's the main reason. So that's going to be a 2 by 2. Okay. And what's the entry of this one? Oh, wait a minute. Here's Ricky. Good deal. Let me get her here. I just can't get my thing down there fast enough. So we got perfect attendance again today. Way to go, team. Unless we got that new person in here and he or she hasn't shown up yet. I don't know if they let her in or not, or him or whoever it was. Ricky, what we're doing, I don't know if you can hear me yet, but we're doing matrix multiplication. Okay? And some of my writing is really bad, and they're laughing that I say some. All my writing is really bad. Just so you'll be able to see, that is an A there. It's a really ugly A. Okay, and that's probably even worse than it was before, but that's okay. I'm not going to go back and check. And what we're doing is matrix multiplication of this matrix B up here by this matrix A here. We've already multiplied A times B, and this is our result, so you'll get to go with us on this one. Now, what I've done to multiply B times A, I write down the size of both matrices. Ricky, can you hear me yet? Yeah, good. Okay. So I write down the sizes. B is a 2 by 2. A is a 2 by 2. And you look at the inner numbers. As long as they're the same, the number of columns of B has to equal the number of rows of A. It does, so I'm going to throw those out. Our answer is going to be a 2 by 2. So now I've drawn the product matrix to be a 2 rows, 2 columns. So that's a 2 by 2. Let's start with the first entry here. This first entry is the first row, first column. So we'll take the first row of B, the one that's listed first, and multiply it by the first column of A, the ones that listed second. So 0 times 1 is 0, plus, you add as you go, 1 times 3. What does that give you? That gives you 3. 0 plus 3 is 3. So that's the first, that's the 1 entry of your product matrix. So what's this position here? First row, second column. So you do the first row of the first matrix, B, times the second column of the second matrix, A. So it'll be 0 times 2 is, say again?
0.
0. And then 1 times 4 is
4.
4. Okay. Now, we go to the next entry. This is the 2, 1 entry, meaning second row here, first column here. So you see the second row of the first matrix, 1, 2, multiply and add the products of the first column of the second matrix, A. So that's 1 times 1 is 1, plus 2 times 3 is 6. 1 plus 6 is 7, I hope. Okay? Okay, it's an ugly 7, but live with it. Okay, this entry here is the second row, second column. So we take the second row of B, multiply it by the second column of A, the second vector matrix you have there, adding the products as you go. So 1 times 2 is 2, plus 2 times 4 is
8.
8. 2 plus 8 is
10.
10. All right, now this is what they want us to observe. Okay? Earlier, Ricky, before you came in, we did the sum of those two matrices, and they were exactly the same matrices. So we concluded from that matrix addition, if it's legal to add, if the two matrices are the same sizes, then when you add them together, you'll get the same answer. Matrix addition is commutative. It doesn't matter which order you multiply, you add. However, what we've just shown is that matrix multiplication is not commutative, because this product here is nowhere close to the same as this product here. So what our conclusion is matrix multiplication, if you can do it, is not commutative. Now, we did these with two little square matrices, 2 by 2 by 2 by 2, and they came out 2 by 2s both in adding and multiply. But if we did rectangular matrices rather than square matrices, let's just say, give me a rectangular matrix, just the size of it. Don't give me numbers, just the size. Something by something.
2 by 3.
2 by 3. Okay, we want to try multiplying that by give me another size rectangular matrix.
1 by 3.
1 by 3. Can you multiply a 2 by 3 by a 1 by 3?
No.
No, they're not the right size to do so. Now, if you had reversed them, you would have had a 1 by 3. Well, that one wouldn't work either, would it? Okay. Neither one of those were. You gave me bad numbers. Who did that? Was that James again? My word, I have to watch that character like crazy. Okay. Let's do the first one. What did you call it before? A 2 by 3?
2 by 3 and a 3 by 1.
All right. 2 by 3 and 3 by 1. Sure enough, you can multiply those two. 2 by 3 by 3 by 1. What would your product matrix be?
2 by 1.
2 by 1. So let's do them the other way. A 3 by 1 by a 2 by 3.
That ain't gonna work.
Yeah, it's not going to work. You can't even multiply them. Okay? So surely you can't commute matrices, especially if they're of different sizes. If they work one way, the odds are they're probably not going to work the other way. So they surely can't be commutative. Addition, yeah, that's commutative. Subtraction, no, it never was. In real numbers, it won't be in matrices either. Multiplication, yeah, multiplying two numbers together, yeah, that's commutative. Multiplying two matrices, no way. Except for special circumstances. We're going to run into some matrices that when you multiply them one way, you're going to get the same answer. Here's what I guarantee. They're going to have to be square matrices. Otherwise, they wouldn't even be the same size. Okay? So, some very special matrices, when you multiply them two different ways, you will get the same answer. Those are very special cases, and we'll pay a lot of attention to. So let's move on to example 5. Okay? So I think I'll clear the screen here. Is everybody on board so far? Any questions? I know Ricky came in late, and Jermanuel came in a little later than James did. So is any of this mystery meat to you? All right. Example 5 is another example of matrix multiplication, but here's something different about example 5. You can see LarsonLinearAlgebra.com for an interactive version of this type of an example. Remember, this author, Ron Larson, has more free, unattached material than any other author I've ever used to teach from, and he has both LarsonLinearAlgebra.com. This is on the back of the book. Absolutely free website. Oh, you can't hear me? He has this one. He also has CalcChat.com. Absolutely free website that you can check your answer for your homework exercises. LarsonLinearAlgebra.com gives interactive versions of some of the examples. And that's what we're going to do now. So if you can't understand what I'm doing, go after class and pull it up at LarsonLinearAlgebra.com. Okay. So here is the first. We're going to try to multiply two matrices together. The first of these matrices is going to be 1, 0, 3. Second row, 2, -1. That's a 1 there. -2. Okay, sorry about ugly writing. Let me go on and see if I can clean that up some. It cleaned up the wrong one. Okay. Yeah, this is a pain in the neck or some other body part. That was a -1, -2. Okay. -1, -2. Hopefully that's easier to read. We're going to try to multiply that by this matrix. -242 100 sorry, I have to drink some more water. Okay, and the last line is -1, 1, -1. That's the -1 there again that ran together, but hopefully you can read it. All right. Now, just looking at those two matrices, would you think that you can multiply them?
Just by looks, she would say, you know.
Yeah, let's do the sizes and see. What's the size of the first one?
2 by 3.
2 by
2 by 3. What's the size of the second one?
3 by 3.
3 by
That's a 3 by 3. So the question is, can you multiply them?
Yes.
Yes, you can. The reason you can is that the two inner numbers are the same. So wipe them out, and what size will your answer be?
2 by 3.
It'll be a 2 by 3. Okay, so that's going to be, and Ricky, you don't have to do this. I just found it helpful for myself to put blanks in there, 2 rows and 3 columns. So I'll know where I'm trying to do things. Okay, your answer has got to be a 2 by 3. So basically I represented what a generic 2 by 3 is going to look like. All right, then I go to the first entry there and see that's the first row, first column. So I'll take the first row of the first one by the first column of the second one. So 1 times -2 is? -2 plus 0 times 1 is?
0.
So that's still -2 plus 3 times -1 is?
-3.
Okay, so -2 plus -3 is?
-5.
-5. Perfect. Okay. Now the next entry here is the first row, second column. So we do the first row here again, but this time multiply it by the second column and go term by term or entry by entry. 1 times 4 is? 4 plus 0 times 0 is?
0.
0. It's still 4. Plus 3 times 1 is?
3.
And what is 4 plus 3? 7. Okay. Now, first row, third column means first row here again by the second column, third column here. So that would be a 1 times 2 is?
2.
2 plus 0 times 0 is?
0.
Plus 3 times -1 is?
-3.
So 2 minus 3 is?
1.
-1. Okay, -1. Perfect. This entry here is the 2, 1 entry, second row by first column. So we do the second row here by the first column there. 2 times -2 is?
-4.
-4 plus a -1 times 1 is?
-1.
So it adds up to a -5 so far, right? Plus a 2 times the -1, a -2 times the -1.
Every -2.
Okay, the answer is -3. It's a +2. -5 plus 2 is -3. Is that what y'all said?
I heard 10 numbers and my head was spinning.
Oh, wait till we get big matrices, huh? Okay. All right. After a while, and I wish you could see this, when I'm in class, I use my fingers and go across and down, across and down. So if you'll follow me when I'm doing this, is the 2, 3 entries. 2 times -2 is -4, plus -1 is -5, plus 2 is -3. Okay. it picks up a little bit if you do that. Row by column, and just sort of keep it in your head without getting too dizzy. Okay, the next entry here, second row, second column, so it'll be the second row here again, this time by the second column here. So 2 times 4 is
8.
8, plus -1 times 0 is?
-1.
Ah!
Hold on. Oh, I did it again.
Okay, who let him into class? Can you tell me that? Okay.
I don't know why every time I get to 0, I be adding, trying to add them.
I know, you don't like nothing, do you? Okay, no, okay, never mind. All right, so I think we wound up with an 8 there, right? 8 plus 0 is 8. And then you have a -2. -2 times 1 is -2. 8 minus 2 is... Did I do it too fast? 6. Very good. Agreed or not? Okay. Now, the last entry here is second row, third column. So you take the second row here again, this time by the third column here, do the products and sums. Okay. 2 times 2 is?
4.
4 plus -1 times 0 is?
0.
0. So 4 plus 0 is 4. And then plus a -2 times -1?
2.
Positive 2, so 4 plus 2 is 6 again. All right. So there we've done the A part here, if I can find it. And our answer, like theirs, is -5, 7, -1, -3, 6, 6. Perfect, perfect, perfect. Okay, let's do the B one. I think we have room to do it. How are we doing on time? Oh, we got plenty of time. Okay. The B one here is a 2 by 2, which is 3, 4. -2, 5. Okay, there's your first matrix. We're going to multiply that by a 1, 0, 0, 1. Whoa, that's an ugly bar, isn't it? Okay, let's multiply this. Well, no, let's first ask ourselves, can we multiply this? What's the size of the first one?
2 by 2.
2 by 2. Okay. And the second one?
2 by 2.
It's also a 2 by 2. Okay. And if you wipe out the second of this and the first of this, the two inner ones, they're the same. Wipe them out. And your answer is going to be a
2 by 2.
2 by 2. Okay, so I'm going to put 2 rows and 2 columns. Okay. Now, this first one here is the first row, first column. So we take the first row here by the first column there. What do you get? 3 times 1 is?
3.
3 plus 4 times 0?
0.
That gives you?
3.
3. Very good. First row here, second column here would be first row here, second column here. 3 times 0 is? 3 times 0 is?
0.
0 plus 4 times 1?
4.
That adds to be?
4.
Yep, if my pen was right. 4. Okay, this is the second row, first column. So we do second row here by first column there. That would be -2 times 1 is?
-2.
Plus 5 times 0.
0.
And that gives you?
-2.
-2. Okay, now we have the second row's second column, so we take the second row here by the second column here and multiply and add. That'd be a -2 times 2 times 0 is
0.
plus 5 times 1 is
5.
and that adds to be 5. Now what do you notice there?
It's the same.
That's the same matrix, and you made me write it twice, didn't you? You did it again, okay? Now, when you're multiplying numbers together, what number is it that you multiply any old number by that number, you always get that any old number again?
It's
the number 1, okay? Yeah, okay, right, okay. Who put him in the class? Okay, no, okay. We call that the multiplicative identity element. Of course, we always called it that, didn't we? Okay. So this is a special matrix here, and this is called the identity matrix. We usually give it the symbol I, standing for identity, okay? And because it's a square matrix, has to be, we usually do the subscript 2. Meaning it's a 2 by 2 matrix. So this is I2. Now let me tell you what an identity matrix always looks like. It's always square. Can't be rectangular. Has to be square. And always the main diagonal from upper left to lower right, every one of those entries has to be a 1. Every other entry that's not on that main diagonal has to be a 0. So it's made up strictly of zeros and ones, but every entry on the main diagonal from upper left to lower right, and it's got to be square, are 1s, and every entry anywhere else other than that diagonal has got to be a 0. That's what the identity matrix is. If that was a 7 by 7, we call it I sub 7. If it was 3 by 3, it'd be an I sub 3. Okay? But it's always every element in the main diagonal is 1, and everything else is a 0. Okay, and anytime you multiply any kind of matrix that you can multiply, this could have been a 7 by 2 by 2 by 2. That could have been a 1 by 2 by 2 by 2. Anything that you would do, you always get the same size over here as that one, and the same entries as that one. Okay? Anytime you multiply, that you can multiply two matrices together with one of them being the identity matrix, you're going to get the same, the other matrix will just replicate itself. All right. Now, let's do another. This is going to be C is 1, 2. 1, 1. We're going to multiply that by another 2 by 2 matrix. This one's going to be negative 1, 2. One, negative 1. Interesting, but do it. First, can you multiply these together?
Yes.
Okay, I did copy it right, didn't I? I think I did. Okay. Yes, because this is a 2 by 2. This is a 2 by 2. When you multiply 2 by 2 by 2 by 2 by 2, you can do it because the inner numbers are the same. Number of columns of one is equal to number of rows of the other. And your product matrix here will be a good old 2 by 2. Because you use the outer of this one by the outer of that one. A 2 by 2. All right. So, let's put in our blanks, blank, blank, and blank, blank. Okay. Now, this first blank here is the first row, first column. So we do the first row of the top one, of the first one, by the first column of the second one. So 1 times minus 1 is?
Negative 1.
Plus 2 times what?
2.
Negative 1 plus 2 is?
2. I mean 1.
All right. Someone else must be getting hungry, okay? All right. We're running out of brain power here, okay. Okay, here we have the first row, second column. So we'll take the first row of this one by the second column of this one. And you get a 1 by 2 is?
2.
2. Plus a 2 times a negative 1 is?
Negative 2.
Negative 2. And what does that give you?
0.
0. Wow, okay. Now, this entry here is the second row, first column. So we take the second row of this one by the first column of this one. And that would be a 1 times minus 1 is?
Negative 1.
Negative 1 plus 1 times 1 is?
Positive 1.
And what does that add to?
0.
You're stuck on nothing, aren't you? Okay. All right. Now, this last entry here is the second row by the second column. So we'll multiply the second row here by the second column there. That would be 1 times 2 is
2.
2 plus 1 times a minus 1 is?
Negative 1.
Negative 1. And 2 minus 1 is?
1.
1. Uh-oh, SpaghettiOs. We wound up with an identity matrix, I2. Now, in regular math, mathematics of real numbers, when you multiply one number by some other number and you get 1 as an answer, 1 being the additive multiplicative identity element, what do you know about those two numbers that you multiply? If you multiply one number by another number and get 1 as your answer, what had to be true about these two numbers? Give me not quite opposite. Give me a number. Just make up a number.
1.
Okay. A little more complicated. Okay, someone's going really easy now. A little more complicated.
12.
12. Okay, that's a lot more complicated, but we can do it. What can you multiply by 12 to give you an answer of 1?
1/12.
1/12. You're absolutely right. So they're called reciprocals of each other. Not quite opposites, reciprocals of each other. 2/3 times 3/2, right? Reciprocals of each other. That's why I was doing my hand like this, okay? Now, this isn't quite what we call reciprocal matrices. We do have another. Another name for a reciprocal is a multiplicative inverse. Just like an additive inverse is a number when you add, you get the additive identity element, which is 0. Well, those are additive inverses of each other. Well, now this is a multiplicative inverse. And that's what we call this matrix. These two matrices here have to be inverses of each other. Why? Because they resulted in an identity matrix, the multiplicative identity element in matrix multiplication. They haven't told us that yet, but you can believe me, I'm telling you the truth, okay? Those are that. All right, let's do number D. I think we've got room here on the slide for that, so let's do D. Oh my goodness, I'm running out of energy. Okay, D is the matrix 1, -2, -3. And you're multiplying that matrix by this other matrix, which is 2, negative 1, 1. Okay. First question always is, can you even do that? Can you multiply? What's the size of this one?
1/3.
A 1/3. You're absolutely right. And what's the size of the second one?
3/1.
A 3/1. Absolutely correct. Can you multiply those two?
Yes, you can.
Yes, you can, because the 3's are the same, so you can wipe them out. And what size are you going to get as an answer?
1/1.
A 1/1, which is just a single number, but because it's a matrix, you still put it in a bracket. So it's a 1/1. It only has one entry in it, so that's the first row, first column. So you do the first row here, multiplied by the first column here, which is only. By the way, what do we call this matrix here? The 1, -2, -3. There's two other names for it.
Row matrix.
A row matrix, or a what?
Row vector.
Row vector. And this one you could also call a
Column matrix.
column matrix, or a
Column vector.
column vector. Perfectly. And when you multiply these two, we're basically got a 1/1, so 1/1, and I think we do. 1 times 2 is
2.
2, plus -2 times -1 is
2.
2 also, so 2 plus 2 is 4, plus -3 times 1 is
-3.
4 minus 3 is
1.
1. Now, you didn't have to have that be a 1. You just needed one element there. It's not always going to be a 1. It could have been a 3/5. It could have been a -4. It could have been a pi-halves. Just a single element. This one happened to be the number 1 as well. Okay? Now, let's take that same problem, but reverse them. And let's take the column vector, or column matrix 2 minus 1, 1, and multiply it by the row vector, or row matrix 1 minus 2 minus 3. Okay? And my question to you now, as always, is, can we do this? What's the size of the first one?
1/3.
Say again?
3/1.
3/1. And you're trying to multiply it by a
1/3.
1/3, right? Is that what you said?
Yes, sir.
Okay. And can you do that?
Yes, sir.
Yes, you can. Because the 1's are the same, you can cross them out, and your answer is going to be what size? Anybody? What are you left with? If you cross out the 1's, you're left with a... Anyone still there?
Say it again.
Once you cross out the 1's,
Oh, that was a 3/3.
a 3/3. So you're going to wind up with a 3/3 matrix. Okay. So that means you're going to have 3 rows and 3 columns, probably more evenly spaced than this. But something like this. All right. This first one is the 1 entry, first row, first column. So you take the first row here, which is the number 2, multiply it by the first column here, which is the number
1.
and what does that give you?
2.
2. These are pretty fun to do because y'all have to add, okay? And here is the row 1, column 2. So you take row 1 again, which is the number 2. This times by column 2, which is -2, and that gives you
-4.
-4. Okay? And then this is the 1, 3 entry. So you take the first row here, 2, by the third column here, -3, and what do you get?
-3.
-6. Perfect. Oh my goodness gracious, I'm hungry. Okay. Now this is the 2, 1 entry, second row, first column. So you take the second row here, which is the number -1, multiply it by the first column here, which is the number +1. And what does that give you?
-1.
-1. Perfect. Anyone want to carry on?
2.
2. Continue. 3. Perfect. Want to go on down here? Anybody? This is the 3, 1 entry. So it would be the third row here by the first column here. That would be a what? 1.
-2.
-2.
-3.
-3. Perfect. 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 Let's see if the book got it right. 2, -4, -6, -1, 2, 3, 1, -2, -3. Yes, they did. Congratulations to them. Okay. So there you've done matrix multiplications when you had identity matrix involved, when you had column vectors involved, when you had row vectors or row matrices involved, when you had inverse matrices involved, all sorts of different ways to do matrix multiplication. They have to fit the criteria though. So, we go back to our system of linear equations. You thought we were through with those, didn't you? Ha ha ha. Dream on. Okay. We are going to be doing these, well, not till the cows come home, but for quite a while. Now, what I want to point out, I don't want to write all this, so I'm going to hold it up so you can see it. Okay. Do you see that system of equations? Doesn't have any real numbers in it. It has numbers as subscripts. That's all. Sum A11 times x1 plus A12 times x2 plus A13 times x3 equals the sum B1, isn't it? Yeah. And then the second row is A21 times x1 plus A22 times x2 plus A23 times x3 equal to B2. And then, yeah, you see it. We've seen those before, okay? Now, what you probably not thought of before, but that could be written as a matrix equation, whereas the coefficient matrix, A11, A12, A13, A22, A21, A22, and A23, A31, A32, A33, that's the coefficient matrix, multiplied by the variable vector, which is x1, x2, x3, and that gives you the column vector b1, b2, b3. Look at that. Do your fingers across the page like I was describing before. A11 x1 plus A12 x2 plus A13 x3 is equal to b1. Yeah, this exactly gives you that. So you can write a system of linear equations as a product of a coefficient matrix times a column vector of your variables, and that's going to equal to a column vector of the constants. That's just another way to write a system of linear equations. And you might ask yourself, why would you choose to? Because they told you to. It's just another way of doing it. Okay? Now, is it any easier than doing Gauss elimination or Gauss-Jordan elimination? Probably not, but it's a way you can do it. And you abbreviate that by capital letter A, that's your coefficient matrix, times the x vector x is equal to the b vector b, okay? So that's how we sometimes will represent a system of linear equation. A matrix, coefficient matrix, times a variable vector usually is equal to a constant vector. Okay. So, example 6 is going to ask us to solve the matrix equation AX is equal to 0. Okay. Where, so that's what we're trying to solve. Okay. Trying to solve this equation. A, so matrix A times vector X. Now, because this is written as a vector, they bold it in the text. Now, you can still call it a matrix, and it is a column matrix, but it's also a oh, look at that. James left and came back. Should I admit him back again? Oh, I guess I already have. Okay. There. Had perfect chance, but I blew it. Okay, sorry about that, Tim. Okay. So, since it is a column matrix, but it's also a column vector, so we'll bold it, and the book bolds it. I write it with an arrow over it. And that's equal to some other column vector, or column matrix B, and because you could represent that as a vector as well as a matrix, I'll put an arrow over that as well. Okay? Now, and we're going, oh, I'm sorry, that wasn't what they had in the book. And you let me get away with it. Shame, shame. That was not just any old column vector. That was the 0 column vector. So, and we haven't talked about that either, but we talked about a 0 matrix. Well, 0 vector is all the elements in that column is a 0, or row if it happened to be a row vector. Okay, so that's what we're trying to solve this matrix. Okay, now given that here is the matrix A. Matrix A is 1, negative 2, 1. I'm running out of juice. 2, 3, negative 2. Okay. All right. And of course your X vector. Now, little word to the wise here. Since your A matrix has 3 columns, the X vector had better have 3 elements in that vector. And it's a column vector, so that's going to be X sub 1, X sub 2, and X sub 3. Now, you don't have to name them that way. You could have called it XYZ, but this is called the X vector. Let's just keep the letter X and add the subscript for the different positions. Okay? And of course, the 0 vector, of course, is the same size vector as that, same number of entries in it that you have rows here, not columns, but rows. Because you see, this would represent x1 minus 2x2 plus x3 is equal to 0. 2x1 plus 3x2 minus 2x3 is equal to 0. So there's only 2 zeros here. Not 3, 2. Because you only have 2 equations. And for this to make sense, this is a 2 by 3, right? 2 rows, 3 columns. This is a 3 rows by 1 column. So this product over here, since the 3's are going to go out, they've been dating. No, I'm sorry, that doesn't mean that. And that gives you a 2 by 1. And that's the other reason, which is really the same reason, that this has to be just a 2-entry model, 2 by 1. All right, so that's your You want to solve that matrix equation. Oh, and I left off this. This is equal to, I said it but didn't write it, the 0 vector. Okay, so our equation that we did here is going to be this. Now this is tiring, but we can do it. Okay. Let's see, 1, negative 2, 1, 2, I can't write, it's an ugly 2, but 3, negative 2, see if I can make this 2 a little better, yeah, there it is, oh man, times this vector here, whoa, that's ugly, x sub 1, x sub 2, x sub 3. Okay, let's see if I can end this a little better than I began it. Yeah, something like that. And that's supposed to be equal to the 0, 0 vector. Column vector or column matrix 0, 0. All right. Now, as we've already said, this is a 2 by 3, that's a 3 by 1, and that becomes a 2 by 1. So that works. So let's do the multiplication. This entry here is the 1, 1 entry, first row, first column. So we'll take the first row here by the first column here, which is the only column here, and that would be this. X sub 1. 1 times x sub 1 is x sub 1. Minus 2 times x sub 2. Right?
Yes, sir.
Okay. Plus x sub 3. And that's equal to 0. Okay? Almost makes you wonder, where is this heading? Okay? Here's sort of what it's doing. The thing we were looking at before started with a system of equations and wrote it as a matrix, coefficient matrix times a variable matrix equaling a constant matrix. We're doing the reverse here. They gave us they gave us an equation, but this was the coefficient matrix, the variable matrix, the constant matrix. We're now making that into a system of equations. So let's do the second row. This entry here is the 2, 1 entry. So second row here, first column here, that would be 2x1 plus 3x2 minus 2x3 and that's equal to 0. All right. Now this feels like we're going backwards, and we sort of are. Okay? How do we solve this before? Gauss-Jordan elimination. Let's do it now. So basically, we write our coefficient matrix, which it seems like we should have done from the very beginning. 1 minus 2, 1. Augment it with the solution, 0, and then do a 2, a 3, and a minus 2, and augment that with its solution, 0, and then do Gauss-Jordan elimination. So, what's the first thing we want to have for a Gauss-Jordan elimination?
A 1.
A 1 in the first position. We got it. We're happy campers. What do we want under that?
0.
A 0. How do we get a 0 under that?
Multiply the first equation by -2 and add it to the second equation.
-2 times row 1 and add it to row 2. You could call them equations if you wanted to, because that's what they are in this case. Okay, so this is going to produce, leaving the first row alone, goodness me, 1, -2, 1, 0. Leave that first one alone. Now let's deal with the second one. -2 times 1 is?
0.
Okay, that adds to 0. -2 plus 2 is 0. Okay, got it. Okay. -2 times 2, -2 times -2 is?
-4.
No, it's not.
I mean +4.
+4. Plus 3 is?
7.
7. Okay, if I could get it right. Okay. And then -2 times 1 is?
-2.
Plus, so -2 is? -4. I don't like the way this is turning out. And I can do the last one. -2 times 0 is 0 plus 0 is 0. Okay. This is really ugly. Oh my goodness gracious. I don't know, my wife says it may be sciatica or something like that. When I sit too long, just like anytime I sit too long, my knee starts hurting because I'm pinching a nerve or something in my hip. So that's why I'm moving around too much. I just can't handle it being here. Okay. Now, we got a 1 here, 0 below it. What do we want to happen next? That's 7 to become a 1. How's the only way we're going to make that happen?
Divide by 7.
Divide by 7. Well, I'll divide 0 by 7. I've already done that. That's 0. And the -4 divided by 7 is going to be a -4/7. Okay? And 0 divided by 7 is still 0. Okay? So this becomes a 1 and that. So we got a 1 here, 0 below it. This becomes a 1. I have it written as that, but it is. We want a 0 above that. So how are we going to make that happen?
You talking about the -2?
Yeah. Yeah, we're going to multiply, -2 to become a 0. We're going to multiply the bottom 1 by a 2. So 2 times row 2. And actually, I realize now, I should have realized it earlier, that I wrote this up here. I should have written it down here, but it worked out. Plus row 1.
Dr. Fowler.
Yes,
Can I ask you something?
Yes, you may.
So, didn't we learn that if we have more variables than equations, doesn't it not apply? Like, isn't it not going to work?
Okay, no, okay. Now let's review that real quickly. If you have more variables than you do equation, you're almost guaranteed to have infinite number of solutions. You're going to wind up with that third column being a parameter. Remember
Right.
T? Okay, that's what we're going to wind up with. Now, if you had more equations than variables, then generally, then that bottom, however many extra equations you have there, are probably either going to wind up no solution or zeros, and that's fine to have zeros at the bottom. Okay. Yeah. Okay, but yeah, that was a good thought. Okay.
Yes, sir.
So let's write that down again. Our second row we're going to leave just alone, except I'm going to change the 7 over 7 to 1. So that's going to be a 0, a 1, and a -4/7. And a 0. Now the top equation, once we operate with this, we'll have 2 times 0 is 0 plus 1 is 1. Good, we didn't want that to change. And then 2 times 1 is 2 minus 2, that's a 0. That's exactly what we wanted there. And then we have 2 times a minus 4/7, which is a minus 8/7, right?
So
Plus
minus
1, which is 7/7, and that leaves us with a minus 1/7 on the top. And I would wind up with more fractions here where I don't have room to write them. Okay? But guess what that last one turns out to? It stays a 0. All right. Now, here's where, since we don't have a leading one in this column here, we're going to have to introduce a variable. You want to call it t. They like t. I like t if it's sweetened. Okay. Let t equal your x3, or x3 equal to, it doesn't matter which way you say it. That's what that third column represents, the coefficients of your third variable x of 3. So that makes x of 1 minus 1/7 t, right?
Yes, sir.
Is equal to 0.
All right.
Okay? And the second one makes it x of 2 minus 4/7 t is equal to 0. And that top one basically says that x of 1 is equal to 1/7 t, right? Just add that to both sides. And x of 2 is equal to is equal to 4/7 t, right?
All right.
And yuck, x of 3 is equal to t. That's where we started.
All right.
Now, I'm going to make life just a little easier. Let's just assume that t is equal to 7. Then, yes, we're out of time?
Yes, sir.
Yeah. Okay. Let me just finish this real quickly. What if rather than t we said 7t? Let's let 7t equal x3. Then you'd have a 7 everywhere, so then you would have t, 4t, and 7t. And that's how the book wrote the answers, where t is any solution, and then you just put in different values for t equals 0, t equals 1, t equals 17, t equals negative 4/3 pi, whatever, and that gives you the answer. So we barely finished example 6, but we'll begin next time with partition matrices, which is something we talked a little bit about before. We're going to do a little bit more now, and then not do much more with it. So that should go relatively quickly, except this is going to be really hard to write. So it'll be miserable writing, but we hopefully will get it done. Okay? Any questions? Okay, I know I kept you 3 minutes late, but you know what? I feel very generous today. I'm not going to charge you any extra, okay? All right. So I will hope y'all have a good weekend. Oh, and by the way, now that you have a test to work on, I don't require you to be sending me any homework anymore, because what I want you working on is the test. Now, if when you're doing and that reminds me, I didn't tell you what homework to do. Thank you for reminding me of that, James. You weren't going to let me get away without it, were you? Okay, you can do either 1 or 3. They're both in the back of the book, rccalcchat.com, for worked out solutions. Any of the odds 5 through 9, they're all at CalcChat. Then do any of the odds, either 11 or 13. They should both be at CalcChat. Then do any of the odds 15 to 27. They should be at CalcChat. Then you can do any of the odds 29 to 35. They should be at CalcChat. And if you want to hold off 37, you can. We'll be talking about those later. Okay? Actually, you could do those. Do 37 if you want to. That's one just like we did. And then any of the odds. Okay, I'm sorry. 37 if you want to, and then you can do any of the odds 39 to 47. And stop there. We'll pick up the rest of those next time. All right. Now, as I was saying before, you don't need to turn in any of these homework exercises unless you want to. And here's why I say it that way. If you're having trouble getting the answers they're having at calcchat.com or in the back of the book, you don't see how they're getting it, please send me those. And we'll either talk about them in class or I'll try to get back to you through email or messages or something like that and see if we can work it out. But if it's just to turn them in, no. You've got your test now. You already got your first test. Be working on the first test. I don't want to drag you away from that. But do your homework, but only turn them in if you're having questions. Okay? If you say, I can't get the answers they got before, I've looked at calcchat.com and I don't understand what they're doing. Something like that, by all means, I want to help you with those. But by and large, once you got your test, that's what I want you turning in next. Whenever you can finish that, turn that in. And any homework questions you have questions about, you can turn those in as well. Does that make sense?
Yes, sir.
Okay, good deal. Any other questions then? Okay, we went about 6 minutes over. I think I'm going to have to try. No, I'm just kidding. Okay. All right, good deal. Y'all have a good weekend, okay?
All right, you too.
All right, doing linear algebra will make it good. I promise you. Okay. Good deal. Take care. All righty. I'm going to end the recording unless there's any other questions. Any other questions? All right. Bye-bye.